Hi everyone, this is the Physics of Light, Module 10, Part 1. Go ahead and get your textbook out and your notes so that you can follow along and write things down. And don't forget that this does not replace reading the text because I'm not going to go into depth as much as the text might go. So I wanted to start, while you're getting your supplies out, with something this other textbook says that I was reading. It's just something to think about. It says, "You may think that when God said, 'Let there be light,' the sun started shining, but that's not what happened. Actually, the sun wasn't created for a few more days after God spoke light into action. What was shining the light then? The Bible tells us that one day we won't need the sun's light. Instead, God himself will be the one who gives us light. Since the scripture tells us one day God's light will replace the sun, we can safely assume that it was his own light that shone on the world during that first day of creation." And just think about how much we rely on God. He is our light, and how much we rely on the sun for our life. So light is like life. I just thought that was a cool thing that I wanted to read you. So now let's get into Module 10. So light is a form of energy, and it travels in electromagnetic waves. Okay, so the last module we touched on transverse waves. And so light is a transverse wave, but it's special because it's composed of an oscillating electric field and a magnetic field, and they're perpendicular to each other. So I guess it would kind of look like this, and then it's going to go out like this. Your book has a much better drawing of this, but they're perpendicular to each other, okay? So light is transverse waves, and there's no medium needed for light to travel through. This means that speed is not dependent on temperature. This is different from the sound waves. Remember, they needed a medium to travel through to vibrate that medium, but as you'll see, light doesn't need that. There's the two perpendicular waves, the oscillating electrical field and the magnetic field. Light travels in a straight line as these perpendicular waves oscillate. So to have light, you must have both of those waves, the electrical and magnetical waves. So how do they keep traveling without a medium to touch and transfer energy? Okay, let me see if I can make this make sense to you. So when an electrically charged particle starts to vibrate, it causes the electrical field around it to vibrate as well. And the vibrating electrical field produces a magnetic field. Okay, so vibrating electrical fields make a magnetic field. A vibrating magnetic field makes an electrical field, and so on. And so they kind of feed each other. They don't need a medium to travel through. With waves that have to travel through matter, there's friction involved, and eventually they slow down. However, no energy is lost through the travel of light because there's no friction. It just keeps on traveling. Light has actually been detected from stars calculated to be 15 billion light years away. That's how far we know light can travel. Here's another thing to just think about. So God created our planet that we live on, and he created these stars that are calculated to be 15 billion light years away. And so that light had to travel 15 billion light years to reach our eye. So does that prove that the universe is that old? Well, not necessarily, because remember that God created Adam as a man, and he didn't need to grow into a man from a baby. So God could have put the light photons from distant stars there, already traveling on their way to Earth. And time may not flow at the same rate in all conditions. And remember that God is not bound by natural laws. So that doesn't necessarily prove that I believe in the young Earth, but just something to think about. So what are electrical and magnetic fields? Remember that like charges repel each other across empty space without touching. So these are magnets. Okay, they're actually attracting. Let's see if I can get them to repel. Maybe. Anyway, they repel each other across empty space. They don't have to touch each other, okay? The positive charge creates an electrical field everywhere around it at all times. Okay, there's an electrical field around this. Whether there's something there to repel or not, there is an electrical field surrounding it. The closer to the charge, the stronger the electrical field, and then it gets weaker the farther away you get. And just, I'm going to note that that's not the same as a force, because it's not a force itself, but can cause a force on other charges. But you actually need two charges to have the force, okay? So it's not exactly the same as a force. So an electrical field is an area in space in which electrical forces can be exerted on other charged particles that enter that space. A magnetic field exerts a magnetic force over an area around it. So thinking about a magnetic field is more like what I was showing you with the magnets. And then the electromagnetic wave's amplitude is related to the field strength, the strength of the field. This would be something that I would suggest looking up a YouTube video on, because it's kind of hard for me to explain and other people do it a lot better. So how fast do electromagnetic waves travel? So in a vacuum, they can move 670 million miles per hour. And remember, sound waves can move about 760 miles per hour. And so that would make light the fastest thing that we know of in our universe. The speed of light changes depending on what substance it is traveling through, and it's actually the opposite of sound. So sound needed to move through something that the molecules are really close together to, right? So sound was fastest in solids because the molecules were so close together and they could vibrate. Well, light is actually the opposite. And so light is actually fastest in the gases. Now, because of this varying speed, light bends as it enters different mediums, but otherwise it would just travel in a straight line. So on page 353, there's a little part called Think About This, and it talks about the Einstein's theory of special relativity, which is E equals mc squared. So the speed of light in a vacuum is the ultimate speed limit of the universe. No object with mass can travel faster than the speed of light in a vacuum. So this equation tells us that energy and mass are the same thing, and they're related to each other by a constant, which is the speed of light, that's c there, squared. So if we have 1 kilogram of mass, we get 9 times 10 to the 16 joules of energy. That's 9 with 16 zeros after it. And that's enough energy to power the whole United Kingdom for a whole year. And that's what gave the scientists the quest for discovering nuclear energy. But the general view of science is that no matter how much energy you expend, you can never travel faster than the speed of light travels in a vacuum. All electromagnetic waves traveling in a vacuum travel at the same speed, because remember, the speed of light changes whether you're in a gas or a liquid or a solid. So all electromagnetic waves traveling in a vacuum have the same speed of the constant speed of light. And I gave it to you in miles per hour previously, but this is probably a better way to memorize the speed of light. So it's 3 times 10 to the 8th meters per second. So that would be the velocity of light, the speed of light. And so if you know the wavelength, you can calculate the frequency, or the other way around, because remember, the frequency and wavelength are inversely proportionate to each other. Okay, moving on. Scientists know that electromagnetic radiation, such as light, travels as a wave, but there's also evidence that it behaves as a stream of particles. So Newton's particle theory of light was that light consists of individual packets of energy called quantum, and we cannot see the individual packets of light, but like a stream of water is made up of individual water molecules, light is composed of individual light particles, energy packets. So a mathematician and a physicist who was Dutch, Christian Huygens, he lived at the same time as Newton, disagreed with Newton's conclusion, and he came up with the wave theory that light is just a wave and not a particle. However, scientists began to do more experiments, and they did indeed find that light behaves as a wave and also a particle. But as they were studying the wave theory, an English physicist, Thomas Young, showed an experiment with the interaction of waves, like if you were to drop things in the water and how those waves run into each other and they interact with each other, and it's called wave interference. Wave interference is when two waves meet, they pass through each other, affecting their amplitude. So it can either increase their amplitude or decrease their amplitude. Constructive interference, so think about in construction, you're building something bigger. When the crest of one wave overlaps the crest of another wave, and their amplitude is combined to form a greater amplitude. So if this wave A combines with wave B, then you're going to get one that is, double the amplitude. This amplitude plus this amplitude equals this amplitude. And that's constructive interference. And then there's destructive interference. So like when you destruct a building, it gets shorter and it's demolished down to the baseline height. When the crests overlap the trough, so here's a trough, here's a crest, the amplitudes cancel each other out, and the result is a wave with an amplitude of 0. So it's just going to be your baseline amplitude of 0. So basically, Thomas Young's experiment showed that light does behave like a wave, and this was 1801. On page 355, it shows this picture, and it talks about how if light did not behave as a wave, then Young would expect to see the light travel in a straight path, but he saw like the waves kind of overlapping and intensifying into these bands, and I highly recommend looking up a YouTube video on how this works because I'm just not going to be able to explain it as good as somebody who does this all the time could. So look up a video on that because it's very interesting. And then in 1887, Heinrich Hertz, so he's who the frequency Hertz is named after, he found something puzzling when he was aiming blue light at a surface of metal. Electrons were emitted from the metal, okay? But when he did it with red light, there were no electrons that were emitted. So this was called the photoelectric effect, and it just puzzled scientists as to how light could cause this if it behaved like just a wave. Like, how could blue light cause that but not red light? A short time later, in 1905, Albert Einstein proposed a new theory called the wave-particle theory. He proposed that electromagnetic radiation, including light, could behave as both a wave and a particle. He argued that when an electron returned to a lower energy level, the energy was given off in packets of energy we call photons. So remember, if this guy gets energy added to it, he gets excited, and the electron comes to a higher energy level. Well, when he goes back down to his regular energy level, it releases a photon, which is light. So a particle of light. And each photon's energy varies depending on the frequency of the electromagnetic wave. So the greater the frequency, the greater the energy of each photon. So blue light has a higher frequency than red light, okay? So blue light has actually more energy than red light. And because the blue light photons have enough energy, or they have greater energy than the red photons, they have enough energy to cause electrons to be emitted from metal, but the red light did not. So when I was reading this, I was like, whoa, is blue light dangerous for us if it can do that to metal? And it is somewhat dangerous. So we've recently begun to make rules prohibiting the sale of some LEDs and blue lights because of studies pointing to them causing damage to our retinal cells in the back of our eyes that leads to vision problems. And there's actually glasses that block the blue light for those who work on computers for their jobs, and you can turn down the blue light on your devices now. So that'll just help you remember that blue light has a higher frequency and more energy. So the currently accepted theory is the quantum mechanical theory of light. Light is composed of little packets of waves, and each individual packet can be thought of as a particle called a photon. Moving on to page 358, the complete range of wavelengths for light for electromagnetic waves is called the electromagnetic spectrum. And it varies from radio waves with wavelengths as long as the size of a building to waves that have very small wavelengths the size of an atom. The frequencies vary as well. Waves per second, remember frequency is waves per second or cycles per second, from low frequencies to high frequencies. The high frequencies, which have a small wavelength, a short wavelength, they don't just bounce off our body, but they can actually move through our body and your soft tissue and then bounce off your bones, and that's what we use for x-rays, or what we use x-rays for. And so because these high frequencies have the small wavelengths and they can get through our tissues, high amounts of UV, X-rays, or gamma rays can damage our cells. Okay, as I go along, I want you to write down something interesting for each type of electromagnetic wave. And I'll tell you what I wrote. So radio waves first. They're right here on the spectrum. They have the longest wavelengths, and so therefore the lowest frequency. They can be the size their wavelength can be the size of a building. And remember, we're not talking about amplitude, we're talking about the wavelength, the crest to crest. And they're used for radio, they're used for TV, and they're used for cell phones. Okay, next is microwaves. So these are about 1 meter to 1 millimeter. They're used for GPS. They're used for weather radar images. They're used microwaves for cooking. Microwaves are basically absorbed by the water in the food. And as the waves go through the water in the food, it increases their energy and it increases the movement of the molecules. And then there's friction that generates heat, and that's how they heat up your food. Next is the infrared. Here's visible light. And so if you remember, Roy G. Biv red would be on this side. So this is infrared, which is right next to the visible light red. So infrared is just, its wavelength is just shorter than microwaves and just longer than visible light. The frequencies are just below visible red light. They are pinpoint size wavelengths, and they are special because they generate heat. These are the heat waves that come from electric heaters, from the sun. Fires produce infrared electromagnetic waves, and also some visible light. Sorry, I said that funny. Fires can produce visible light and infrared electromagnetic waves. We cannot see infrared light, but we can feel the heat from it. And then there's thermographs that can be used to find missing people by visualizing their body heat on a screen. And so it's just detecting the infrared waves on a screen. Then there's visible light. So remember, white light is all visible light wavelengths combined. So Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. And they go in this direction. Red here, and then violet is the highest wavelength. Shortest wavelength, highest frequency. And here's just a little fun fact. Isaac Newton discovered the visible spectrum that we can see and included both violet and indigo so that the spectrum would have 7 colors instead of 6. He was a strong Christian and believed 7 was a more spiritual number. So the spectrum includes indigo and violet, but to our eyes, these shades really just blend into one. And if you use a prism, you can shine white light on the prism. White light is what comes from our sun. The sun has all the visible wavelengths in it. So you shine it on the prism or through the prism, and the prism bends the light, and then it separates out the wavelengths, and then you'll actually see all the colors of visible light, the rainbow colors. The red is the longest wavelengths of visible light, the lower frequency. And the violet is the shortest wavelengths, the higher frequency. And I remember that because, remember we talked about blue light being dangerous because it's a higher frequency and it's a shorter wavelength. It can go through our tissues. Well, violet's right next to that, so I just remember it like that. Visible light wavelengths range from 1/100th the thickness of a human hair to the length of a bacterium. So they're getting smaller. The different colors of the rainbow have different temperatures. So scientist Herschel, he put light through a prism and he spread out the wavelengths, and he noticed that when he measured the temperature of the different lights, and as he was measuring these temperatures, he also discovered that there was heat, that there was an increased temperature past the red light that could be measured, leading to the discovery of infrared light, invisible radiation beyond the red that we didn't know existed. I struggled to talk to you guys about this just because I struggled with the blue-violet light having a higher frequency. It has more energy. So why did Herschel's experiment show red light having a higher temperature? And what I could find on the internet was that when the blue light was bent through the prism, the blue light was scattered more, and the thermometer for the red just absorbed more light particles, leading to a higher temperature because the blue is more spread out from a prism. But if you guys want to do more research on that yourselves, go for it. Okay, so Herschel began the discovery of infrared light. Let's talk about the other side of visible light, where the frequencies are getting higher, the wavelengths are getting shorter. So we have ultraviolet light, and it's above violet, so ultraviolet. It's a higher frequency than the violet light. So the wavelengths are getting shorter and there's more energy in them at that higher frequency, and they can actually kill living tissue, the ultraviolet light. So UV lamps are used to sterilize things. If you go to Winco, there's these really big water bottles you can refill, and there's a light underneath as you're refilling them, and that's a UV light to kill any bacteria. But UV light can damage our eyes, so we could wear polarized glasses, and we don't look at the sun. We lessen our exposure to the sun with sunscreen. However, we do need some sun on our skin because the sun actually helps us produce vitamin D in our bodies, and it helps us absorb calcium into our diet. Cool things about ultraviolet light are animals can see ultraviolet light. So insects can see UV light on some flowers that attract them to pollinate those flowers. Bees can see UV light, but they cannot see red light. Deer, they can't see red or orange. We're getting away from ultraviolet light here, just some cool facts. So deer can't see the visible light, red or orange, and that's why hunters wear orange when they're hunting deer, so other humans can see those wavelengths of light, but the deer can't see those wavelengths of light. However, one thing that I want to note is that if you're going hunting and you use laundry detergent that had UV brighteners in it, then the deer can still see that on your orange clothing. So I guess just don't go hunting with any gear that's been washed in soap. Just kidding. So on the other side, I'm talking about infrared now. Snakes and other reptiles can detect infrared light. They have heat sensors to find their prey. So whatever's warm, they can actually see that. Heat-seeking missiles seek out infrared heat coming from other missiles to destroy them before harming people. Night vision uses infrared technology. Infrared technology can also be used to see through paintings to detect anything that was painted underneath the visible artwork. Okay, so back on the other side of visible light is the ultraviolet light that we were talking about. So we have ozone, which is O3, in our atmosphere. And it's actually formed from O2, oxygen, O2, by the energy of the UV light and electrical charges in the Earth's atmosphere. So if you were to see ozone by itself, it's a pale blue gas, and it actually has a bad odor. So there's this layer of ozone around the Earth that's kind of like a filter, because the ozone breaks down into O2 as it absorbs the UV light. So the 3 oxygen molecules, the ozone, break down into O2, and they absorb the UV light, and that protects our cells from a lot of damage. So we need that filter. But it's nice that it's a filter, because the light that we do need, like visible light, is still filtered through. And it doesn't filter out all of the dangerous UV rays, but a lot of it. Okay, so that was UV light, ultraviolet light. Now X-rays, higher frequency waves, more energy than UV waves, and they can pass through our soft tissues, but our bones can stop them from passing through. So we can actually use them to make images, bone imaging of our skeletons. And do you remember how we get images of soft tissue? So for soft tissue, we use ultrasound waves, not light waves, but sound waves. But X-rays, so they're getting the smaller wavelength, higher frequency, more energy. They're actually dangerous if we get too much exposure to them. So we have to limit the number of X-rays that we have, and we have to cover the parts of our bodies with lead that are not being X-rays to block those waves from damaging our other tissues, cells. Keep going even higher, we have gamma rays. These are the shortest wavelengths. They're shorter than the diameter of the nucleus of an atom. So they can penetrate just about anything, but they're very dangerous. They're very damaging to us and our cells. However, they are used to target cancer cells and also to make color-coded images of the brain. So light behaves differently when it strikes an object. It can go through it, it can be reflected by it, it can be absorbed by it. If something's transparent, light passes through it. So this is saran wrap, and light can pass through that, and I can see the image on the other side. Now if it's a material that's kind of wavy, I can't make it very wavy, but let's talk about the glass there. See how it's kind of wavy and the image on the other side is fuzzy? That's translucent. So translucent materials are materials that allow light to pass through, but it scatters the light waves and it results in fuzzy images. And then you have something that's opaque, and this is going to either absorb or reflect all light that strikes it. So I got tin foil to show you that. So those are the three things there. And then we'll pick up part 2 on the same page, talking about the interactions of light down there. So I want you to do all of the on your own questions up to 10.5. And if you get stuck on any of these concepts, please look up more videos on the internet, on YouTube, whatever. Get more books on it so that you understand this, because I'm a little bit limited in how I explain it. I hope I explained it well enough for you. All right, thanks for watching.